Hello, everybody. Welcome to an impromptu virtual lecture on applied optimal control. Hope we're doing great. The good news is I have so much I want to code with you all today. I mean, we're just getting into the thick of these multi-body ARM controllers. And yes, I would love to be in person with you all today talking about the virtues of LQR, and that will happen. My goodness, I want that to happen. But yeah, but I got to say, there's something fun about coding up an operational space controller. So again, just as a review here, what we're gonna have, and so when we last coded, actually, let me pull up my code from last time, which is now up on Canvas. If you want to download it, in case you didn't follow fully along with it, it's now up on Canvas. I'm gonna pull up the code. This was our code from last time. The sim double pendulum is what it was. All right, here we go. Let's change the folder. There's our sim double pendulum, friends. And what is it doing? It's deriving the equations of motion of a pendulum, a swinging pendulum attached to another swinging pendulum. And it derives those equations and it simulates them. Okay, we set that up. We set that up last time. Now, there we go. You have this twirly whirly plot. Hopefully, you can see these are the two pendulum angles swinging around. We started off in like a swinging position, and they all kind of doodly-doo swing around, right? Now, you're kind of trusting me that I did a good job, and in fact, it looks like the real pendulum dynamics. One thing that we learn in mechanical engineering is we try to check if it's working well. It's good to kind of show an animation of it. It's a fantastic check. There are other things you can do to make sure that your system is working correctly. A great one is if you have an energetically conservative system, like we do, we could check to make sure that energy is in fact conserved. We could add up all the kinetic energies and the potential energies, add them all up, and it should be constant. We don't have any friction or anything in this model of a double pendulum. We can check it. It works. But in absence of that, just for the sake of time, and also because it's more awesome, we're going to simulate a double pendulum. We're going to like animate the double pendulum. Okay. But anyway, I'm getting ahead of myself. Okay. So, what the goal is though, bigger today, is take this little pendulum. So imagine this is the hinge of my pendulum. This is the hinge of my second pendulum. So I got like my shoulder and my elbow, right? That's like a robot arm. Okay, like I'm not a robot, but you get the point, right? And so what we're going to then do is we're going to take this otherwise floppy, energetically conservative system. We're going to put motors on it. Okay, motor here, motor here. We talked about doing this in class. In our lecture, we talked about how we would add the torques to the right equations, so that way we can actually put motor torques on it, like a real robot, like a real actual controlled actuator. And then what we're going to do is we're going to put a controller on those torques, okay? In such a way that we're going to control the end effector, okay? That's the end of the robot arm, my fingers here, okay? And we want to be able to control it so they go to a particular point, and specifically that they accelerate directly in that direction, right? Okay, so we're going to work toward what we call an operational space control, okay? Operational space controller. And that might take yet another lecture to get done correctly, but it's so cool when it works. I'm sorry, it's just so neat because that operational space, the idea is that is your task. This is the thing that we actually care about maybe for a task for a robot, is where are our fingers? Okay, I was gonna actually bring in my son as an example here, but he's down for a nap right now, and at least for the time being. He's theoretically down for a nap at the moment. But if I put something out in front of him, he loves grabbing things. Okay, say he's grabbing for this, right? And his little baby hand is right over here. Okay, he turns 1 today. All right, little baby hand is because tries to grab that. The task is because he wants to grab this thing, right? So we will define the task as being the end effector of our arm, and we're going to command accelerations of that end effector in Cartesian space, meaning X and Y. So it goes directly toward that thing, right? Okay. And the beauty of it is that we don't need to tune up gains for individual joints. We don't have to put a PD controller here and a PD controller there. We have to tune up the gains appropriately to get them right. And that would change with the mass of the arm and everything. Because the operational space controller is aware of the dynamics, we just tell it how we want it to accelerate, right? Okay, that's the big picture. That's what we want to accomplish today. But in order to get there, I think it's going to be useful for us to actually see what this robot arm is doing. Okay, like an animation sense. That's what I was talking about. So I would love to animate this now currently unactuated robotic arm. It's going to flop around. Let's see the flopping. Okay, so let's go. So let's go back to our board. Okay, today where's my stuff? Where's my stuff? Okay. All right. Come on. All right. So today, 2026 04 14. Okay, we're going to move toward the operational space control. Or OSC. Okay, we're gonna for this robotic arm. Okay, so we're gonna do a few things. We're gonna try to do an animation. That's gonna help us see what's going on with this robot arm in a way that's more intuitive than just seeing angles, legs flopping around, and it's just neat. Okay. Then, as a step in the direction toward operational space control, we're going to do to put together an inverse dynamics controller. Okay. And the idea here is that we're going to have some commanded acceleration. So Q double dot desired, right? And that's going to give us our torques. That's what inverse dynamics is. Inverse dynamics is saying, hey, what accelerations do I want? What are the torques that will get me that? Okay. Forward dynamics is the opposite. We apply torque and we see what happens, right? So that's inverse dynamics, as we've talked about before. And then we're going to try to do an operational space control. And this is going to have us actually setting up and solving a quadratic program. Okay. QP. Inside of the control loop. So we got a few steps to go here. Okay. So let's go back to our, before we get back to our code, let's recall we have our double pendulum. And double pendulums are really neat. They're chaotic, and basically, if you take two double pendulums that are identical, okay, and you start them off in an initial pose, and then you drop them, right, and one is only slightly different from the other, okay, it's gonna eventually flop around in all kinds of crazy ways. Any question? You got a question, Jewel? You got it. You got it. So so they will eventually diverge. Like it'll flop around in one direction, and the other one will flop around maybe in the other direction. It'll look wildly different. Okay. In fact, back in the era, I remember when I would follow a lot of people on Twitter who did science stuff. There were automatic accounts, bot accounts that would every day just take a pendulum, start it in a random initial condition, generate a video, and post it to Twitter. It's one of my favorite accounts to follow, just because it's hypnotic to watch. So let me stop talking about how hypnotic it is to watch, and let's actually show how hypnotic it is to watch. So what we're going to need to do, so just remind us, okay, that this is our double pendulum had these. Okay, it's written up like this. You have it under gravity. You have a pin joint with no friction, and then you have a mass. That's mass 1. And then you have a second mass that's mass 2. Okay. And there's length 2 and length 1. Okay. That's theta 1, time varying, but I think you know that. And here's theta 2 that's also time varying. Okay. It is relative. The first angle is relative to the vertical. The second angle is relative to the first angle. Okay, which is why when we were setting up our kinematics, we said that the position that when we had some vector R1, called R1 hat, and then R2 hat, right? We said that R1 was equal to is equal to L1 sine of theta 1, comma minus L1 cosine of theta 1. That is just pointing downwards, pendulum pointing downwards. When it's 0, cosine of 0 is 1. That means it's minus L in the positive direction. Sorry for bumping my mic. Oh my goodness. Oh, what a heck of a day. Heck of a day. Heck of a day. All right. And then that's in the horizontal direction. That's the sine of that angle. That's just your trig, okay? And that R2 was equal to R1 plus this angle here, right? So in that angle is going to be, this is a little vector notation that you used from calculus 3. When did you use the vector notation? Anyway, plus L2 sine of theta 1 plus theta 2. In case it isn't obvious, these angles are both inside of the trigonometric function. They're both inside. And here's L2 cosine and minus L2 cosine of theta 1 plus theta 2. Now, all right, so basically, these are our kinematics. This tells us where our masses are. Boom, boom, boom. And we're going to use that to draw our pendulum. Okay, so for our animation, we're going to need to draw where these things are. Okay, we're going to draw a little stick that goes boop, boop, boop with a little elbow using these points right here. Okay, and then we're going to draw little masses. Oh, shoot. We're going to draw little masses, happy little masses, M1 and M2 as little circles, just as a simple little animation. We can do fancier ones, but we're limited in time. But unlimited in fanciness, I would say. Okay, so now, let's go back to our code. All right, so right now, if I go back to my code here, this is what we ran before. Okay, this is sim double pendulum. You can grab this off of the Canvas page. The files page is right there from last lecture, I believe the 9th. And what it does, it drives the equations of motion and simulates them. Look, there is our ODE45 function. That's our simulator that's simulate our system, right? Our system. Now, one thing you're going to notice, by the way, is that if we want to simulate this every single time, we're going to run all of these symbolic calculations that we're doing the Lagrangian dynamics, right? But if our dynamics aren't changing, we don't have to do that every time, right? And it's a little annoying. Watch when I run it. It's going. It's not that long. It's actually not that bad. Okay, but what you could do is you could run a script that just drives the dynamics, then run a separate script that runs the simulation, and a separate script that runs the animation. Okay, maybe here it won't be so bad, at least on my computer. Well, this computer is like got in 2019. It's almost 7-year-old computer. So if my computer, it's not a workhorse or anything. My computer can do it. Your computer can do it. I think you're okay. Let me know if you're having much longer running times with your code after you run it once. The first time you run things in MATLAB is a little slower. Okay, simulate our system. So now we're going to animate our system. Okay, now you'll recall that. So what are we going to need? So we're going to need to define a few things. So we're going to have to create a new frame. We're going to create a new figure for our animation. Okay, so let's say figure 2. This will be figure 2. All right. We are going to want to have an animation loop. Let's see, and we're gonna have a certain number of frames per second. Okay, let's just do 20 frames per second, friends. Okay, so frames per second in animation. Okay, and we're not gonna do the thing where we save the video just yet. We're just gonna play it in the real time so you can see what's happening. Okay, all right, so frames per second, and so what we need to do is have a time point. So we say we need time points for every animation frame. Okay, we'll call that T_anim, T_anim. All right, and so that's going to be between 0 and whatever our final value of T out is. So our simulation gives us a T out. Let me just make this a little bigger. All right, T out. So it's going to be the last element of T out. Okay, T out end in MATLAB here. Okay. Now, in increments of what? Well, there's 20 frames per second, so every frame is 0.05 seconds, or 1 over FPS. So in intervals of 1 over FPS, done. Okay, that's going to create all of our time points for every animation frame. So we're now going to have an animation loop. animation loop through every frame. Not so bad, right? So we'll have some iteration. For iter is equal to 1 colon the number of elements in the animation in the animation time vector here. So it's going to loop through every time point, right? We want to plot the current frame. So one thing you can do is first thing you can do is you can clear the axes. Clear the axes. So we're gonna clear the axes. You're gonna wipe them clean, and then we're going to plot the actual animation. We're actually then we're gonna plot our frame, and then we're gonna draw it, and then we're gonna pause for a little bit. Then we're gonna clear it. So we're gonna draw it. Say, hey, there's our animation frame. Clear it. Do it again. So then we're gonna watch it. You know, all in a loop, right? Okay. So we cleared the frame. So let's define the things we want to plot. Okay. What are the things we want to plot here? Let's pull up there's our pendulum. So what I'm going to want to draw is just, for starters, I'm just going to draw a line that bends here. So really it's just point here, point here, point here. But those points are defined by our vectors here. So we can find out, hey, what is R1 and what is R2? In order to do that, we need to know, hey, what is the current value of theta? And what's the current value of theta 2, theta 1 and theta 2? So let's grab those. And the way that we grab these in the past, as you did in your various assignments, okay, is through interpolation, because this T out, let's look at T out right here. What's T out? Well, T out is this big old vector here. And the simulation decides where these time points are, right? And they might not be on any of our animation frames and exactly intervals of 0.05. It's not there, so we use an interpolation, right? So let's do a few things. Let's interpolate our. And see, let's interpolate our animation angles. All right, so let's call it theta 1 interp, or theta 1 animation, A-N-I-M, theta 1 anim, okay? And all we need to do is do a one-dimensional interpolation, interp 1, and we say that, hey, our time points are T out. They're all in that vector, okay? Now, our angles are in our simulated, X out, okay? All right? And it's going to be X out, and our first X out, and it's going to be our first column, because our first column is our first state across all those different time points. That's how ODE45 gives you your state vector back, your states back. So colon, comma 1. Okay. Now recall, just for our purposes, I'm going to put it off in the corner here. We have our X of T. That's our state vector. Okay. Has 4 elements. Okay. The way we framed it up this time is that the first state is theta 1 of T. Our second state is theta 2 of T. Often we would go theta 1 dot. Here we just did theta 1 theta 2. It was just easier to fit into our code that way. It doesn't matter which we choose as long as we know how we defined it, right? So this is going to be our first state, our second state, and then our third state and fourth state are, of course, theta 1 dot of T, theta 2 dot of T, right? Okay. So back to our code. All right. So that's just a reminder that it was our first column, colon, comma 1, every row, just the first column. That's all of our theta 1 angles. All right. I'm going to copy this, paste, theta 2. That's going to be our second state, so it's our second column, right? We already talked about this. That is our second state. Whoop, whoop, there it is. You got it. All right. So we have them interpolated. Oh, awesome. Great. Cool. Nifty neato, right? So now we've cleared our axes. Now, and at a given, theta is equal to 1, equals 1 colon num L anim. No one caught that. Okay, I won't take it personally. Okay, so now we're going to define our theta 1. All right, for this particular point in time is going to be just iterating through our current animation frame. Let's see, did I call theta 1 anywhere else? I did not. We're all in the clear. Awesome. So theta 1 is going to be equal to theta 1 annum at the current iteration, the current frame. Okay, semicolon. And we'll do the same thing with theta 2. Theta 2. Theta 2 annum, right? Okay, so now let's define R1 annum. Where we're going to animate. Okay, this is this vector here, R1, and that is our L1 sine of theta minus L1 cosine of theta. So let's make this as a column vector. Just we're finding ways to put this all together. Boop, 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 boop. All right. Okay, we're going to say L1 times sine of theta 1. Thankfully, we're always dealing in radians, so this makes everything easier. Say minus L1 times the cosine of theta 1. Nifty, right? Okay, that's the current R1 annum. Now R2 annum is going to be equal to R1 annum, right? Just right there, plus that. Okay. Plus vector. It can be a column vector with two elements, L2 times sine of theta 1 plus theta 2. All right, semicolon, minus L2 times cosine of theta 1 plus theta 2. There we go. That's the end of that line there. Great. So this R1 is our vector here. R2 is our vector there. Okay, and if we want to plot boom, 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 and connect them, we're just going to need 3 points. We're going to need, this is going to be 0, 0. Okay, right up there. So if we, let's do a quick plot. So let's plot our connecting rods, you know, for the double pendulum, right? So it's going to be a couple things. So what is it? It's going to be plot. So what are our x points of our rod? Our first x point is going to be 0. All right. Our second x point is going to be R1 annum as the first element, right? And then it's going to be R2 annum, the first element, right? That's just the x, that's the x coordinates of each of these vectors, right? That one, right? So 0, that. Then for our y coordinate, it's going to be 0, that. And that should draw from 0, 0 to there, right? Okay. So that's our x points. I'm going to copy this whole thing, this little vector right here. Okay. We're going to paste it. And it's the same thing, except it's the second element for the y coordinate, right? Okay. All right. Now, black line, right? So black line, we're going to connect to the black line. Now, I like to add things like a line thickness. Let's make this a thicker line. So what I'm going to do is I'm going to do an ellipsis, ... move this down to the next line. I'm going to say, yes, it's a black line, my friends. But I also want the line width to be, let's say 3. Okay. All right. Now what I'm going to do is I'm going to say draw now and end the loop. And we'll just see if this works, okay? This is not going to work exactly right. Okay, it's going to probably flop around. The zooming of the plot will be weird, but we'll get to that as to why in a second. Okay, are we done? Okay, did not show the animation. Did I not plot it correctly? I draw now. Okay. It should have shown me something. Do I need a hold? I'm not sure I need a hold. I can try it because I'm only plotting one thing. It's a good thought there, Marco. Let me just, here's what we're going to do. We're going to do pause. The pause command by itself will just wait for a text input before like the enter key to move forward. See if it works. It's a good debug command, is adding the pause command. So, all right, it's not plotting anything. Why is that? We're in figure 2. Did it plot somewhere else? Yeah, there's no hole. We cleared the axes. We plotted. Let me just, okay, let's control C to get out of this because you got it right now. We got to control C. It's in the middle of the code. I don't know why it's not plotting. Maybe it could be. Actually, let's look what's in R1 anim. Maybe my math is weird. R1 anim. Oh, there we go. That's the key. Not a number. What? What? Okay, so that must mean our thetas must not be a number. Let's check out theta. Theta 1. Not a number. Okay. What's in theta 1 anim? So it's plotting not a numbers. There's your problem. Okay. Theta 1 anim. Let's look what's in there. Theta 1 anim. What's in there? Lots of not a numbers. I don't like that. Okay. What did I screw up here? Okay. Well, what's T out? T out. Great. Oh, you know what? I forgot a complete. There's a third input to our interp 1. It's the time points that we want, and no one caught it. I'm disappointed in me. Okay. We want to know what it is at the T animation frames. Okay. T animation frames. Silly me. Save that. Okay. All saved. All right. So comma T anim. Comma, let's see. Comma T anim. Comma T anim. All right. Now let's check that out. Let's get rid of this pause. We do not need it right now. Let's see what happens. Okay. Yeah. It's drawing something. Doing weird things. What's the problem? The problem is that the zoom is not consistent. The axis limits are not consistent. So what we need to do is make sure the axis limits are consistent. So we're going to say axis, open parentheses, and I believe we should be, if we go minus 2.5 to 2.5, because this is both the lengths I believe are 1. Okay. And then minus 2.5 and positive 2.5. That way it's maximum 2 on one side, maximum 2 on the other side. Gives a little buffer of 2.5 on each. And whenever you're plotting something in Cartesian space, well, I'll show you what happens when I do this here. Again, every time we're rederiving these, oh, look, not bad, right? Hey, look, it's swinging around. See that? Not too bad, right? The only thing I don't like about it is that when you squish this, you squish the plot. Like, that doesn't look right. That ain't right. Both of those lengths, I believe, are they the same? Yeah, the lengths are the same. So, but they look different. And that's because I'm pretty sure that's an aspect ratio problem. Okay, so what we're going to do is we're going to fix the aspect ratio to be equal by saying axis equal. Okay, see how that works. Not bad. Hey, look at that. I did screw something up real quick. Technically speaking, you want to put axis equal before the axis limits, because what then will happen is it'll first set, hey, I want the axes, like 1 unit in the x-axis to equal to 1 unit on the y-axis when we're plotting it. So it looks like, a square looks like a square. All right. It doesn't look like a squished rectangle. And then you set the axis limits and it crops it off. So this should do it. Look at that. There you go. Nifty, right? We got a swinging pendulum. Now, if I want to add additional features, I want to add like circles where the masses are, which I totally can add. I'm going to add them right here. For this, Marco, we will need our hold on. Okay. I'm going to plot. Okay. And now I'm going to plot our circular masses. All right. So I'm just going to plot them as, frankly, these exact numbers, but I'm going to cut out the 0. I don't need to plot a mass at the origin. So I'm just going to grab these two. Copy, 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 copy. Boom. Comma. Same thing, except I want the second element. So I want 2, 2. And I want to have, let's do a red. Let's do a black circle. So KO, lowercase ko will give us a circle. But we also want to change the features of it. So let's make the marker size. I believe it's called marker size. Make it larger. Make it 10. I forget. Let's try that. And let's set the marker face color. Marker face color. Let's make that red. So we can do, I think R will do that. I believe that will work. Okay, set the marker size to 10, marker face color to red to be fun. There we go. Doesn't look bad. See that? I want to make sure you can see the actual code as well. Excuse me a second. So you see the code, and you can see my fancy pendulum. I'm gonna make those masses even bigger. I'm gonna make them like 13. Okay, just so they look bigger. Okay, everyone getting that? Anybody getting that? Look at that. Boom. Nifty, right? Swinging pendulum. Now, my friends, I said it can get wacky what these pendulums look like they do, and I stand by that. So I'm going to change the initial conditions so hopefully cooler things happen. So where's my initial conditions? I set them before our animation loop. We set our initial conditions here, right? These are our initial conditions. Rush through the end there. Okay. All right. So I'm just let's see, pi over 4 is our current ones. Let's try 3 times pi over 4 and pi over 4. That should be mostly upright, and the other one is upright, if my math is correct. So let's run that, see what it looks like. Whoop. Yep. Okay, not bad, not bad. I can get it to do fancier things, I'm sure. Okay, I can do things like change the masses. I want to get that end of that pendulum. I want that flipping around. I want to doing little twirly whirlies, to use the technical term. So if I make that lower mass that smaller, right now M2 is 2. I'm gonna make it lighter. I'm gonna make it 0.5. Okay, M2 is now 0.5. I think this will make it go really swinging around in fun ways. Let's try it. There we go. Look at that. Fun, right? And right now it's only simulated for 5 seconds. You can simulate for longer to watch the fun happen. Let's watch that one more time, just because life is short. Watch a double pendulum. Neat, nifty, cool, awesome. So we have an animation that looks like a double pendulum to me. I think we did it right. Okay, so now we got to get to the point where we're doing control. We got 40 minutes to do some control. Let's see if we can get through at least inverse dynamics, which I believe we can, friends. I believe we can. Anyone getting that? Anyone need to see any code? Anyone need me to copy any code in there? Tell you what, just because I'm nice, I'm going to copy the animation code in here into the chat. Boom, got it. So we have an animation. So now back to our board here. We now want to do some inverse dynamics. Okay, that's what we want to do next. Okay. All right. So we got some inverse dynamics. So what do we need for that? So let's recall from inverse dynamics. Or ID. Okay. The idea is we want to say, hey, here's our Q double dot desired. We want to get out a tau. Now, if you look at our equations of motion, the way we formulated them is that we have some m of q times q double dot is equal to everything else. F of q, q dot, and tau on the other side, right? We already solved for that, but we don't have any torques currently in our model. That's the one big thing. We don't have any torques on our little robot yet. So let's add some torques, okay? And how are we going to add those torques? Well, let's go back to our code. Okay. If we look at, currently we have this left-hand side that we have of our Euler-Lagrange equation. That's the left-hand side we have over here. And we want everything else to be on the right-hand side. That's F, right? Okay, so what we need to have is we need to have on the right-hand side, we need to have these torques. Okay. So the way that we set this up before is that we have our equations of motion. Our first equation of motion is going to be pertain to theta 1 theta 1. And our second equation motion is theta 2. Okay? And if you look at our actual EL equations, let's look at EL LHS just to show you what's in it. Okay? Yep, that's what it looks like right there. And so it's a vector which has two equations in it, right? So that's all on the left-hand side. But right now, on the right-hand side, I think we said our right-hand side is equal to 0. We actually didn't say anything about our right-hand side, okay? We need to define our control inputs, tau, okay? So what we need is we need some new symbols, okay? Our new symbols, we're going to say our two input torques, we're going to call tau 1 for our first input torque, and tau 2 for our second input torque. These are our input torques, okay, for our two motors. Okay, if we set those torques to 0, it should behave exactly like our passive pendulum, right? All right, so we're going to have our theta 1, we're going to have our Euler-Lagrange left-hand side. Okay, is going to be equal to our external torques. Okay, these torques that we're applying. So if we're going to apply tau 1 to our first angle, right, to our shoulder, right, our tau 1 is going to show up as these non-conservative forces. Okay, and then here's our EL LHS for theta 2, our left-hand side, right, and we're going to have tau 2 at our elbow. That's going to be applying a torque to our second degree of freedom, which is our theta 2, right? Okay. Now, the only thing that we talked about in previous lectures is that, don't forget, Newton's third law still exists. Even though we're doing Lagrangian mechanics, it still describes actual real life forces and actual real life control laws, okay? So that means there's an equal and opposite torque on our first degree of freedom. Why? Because that motor would be mounted to my upper arm, okay, and then connected to my lower arm. So it's right at my elbow. So any torque I apply to my elbow, I get equal and opposite torque to my upper arm, okay? So in our first equation, we have that. This is our right-hand side. EL RHS, right-hand side, okay? So where do we add that in? So right now, we are very fortunate is that everything on the right-hand side, F, is now put on this F right here, okay? That's the right-hand side. So since we already did all this crazy math and such, let's just add to this. I'm just going to put in a different color. We're going to add to this tau 1 minus tau 2 and tau 2, okay? And that should work okay. Technically speaking, like our F is dependent upon tau, but you can see what we're kind of doing here, right? We're making F now dependent also on these taus. So let's add it to this term right here. Let's say plus. And it's a vector. We're going to add this vector right here. So in the first column, the first row, it's going to be tau 1 minus tau 2. And then the second row is going to be positive tau 2. All right. Now that's going to define our force F. Now, one thing you got to note, though, is that our function for F, this F function, we specifically said should be dependent upon which variables? Q and dq. That's q dot, right? But now, my friends, we also want it dependent upon tau. So we want to make sure we pass in to our MATLAB function command our control input, our control torques tau. Okay, so we can add. Here's how we'll do it. Let's say, where do we define tau? Up here, right? Okay, perfect. I'm going to say that the vector tau is going to be equal to tau 1 semicolon tau 2. So that way it's a vector of two elements right there, right? Okay, all right. And so now I'm going to make it dependent upon tau as well, right? Okay, so now whenever I call f func, which is what we do for our dynamics, right? We try to solve this. Where's that equation? Where did you go? Where's that equation? This equation for q double dot, we now have to put Taos in there. Excuse me a second, friends. Okay. Okay. I need to my dog is getting into trouble. 1 second. I'll be right back. Let me turn on the be right back screen. All right. This little guy trapped himself in the bathroom. How he did that, I'm not exactly sure. So hopefully it didn't make too much noise for you all. But this microphone's pretty sound isolating. So anyway, hope it worked out fine. All right, chill out with me. Chill out with me. We got a carpet right here. Chill out. All right, where were we? So we had just added tau as one of our inputs to F. Perfect, right? Because there's our F right there. So now whenever we call our dynamics, where do we set that? Oh, look, there's our dynamics right there, right? It's dependent on, here we go, here's our F func, where we send in our Q's, there's our Q. And our DQs, those are our velocities, DQ. Now we need to send in our torques. So if I send in our torques as being 0 and 0, 0 semicolon 0, right here as our third input to F func, right? Okay, this should all theoretically still work. Let's try running it, okay? It'll run exactly as it did before, but with no torques, but with 0 torques at those 2 joints. Okay, so let's see how that works. Okay, I'm looking at it, and it looks like it's basically the same. Okay, all right, that looks like it's basically the same, but let's actually test it out. So like, let's try actually applying a torque. Okay, so what I'm going to do is I'm going to try to apply a torque at my shoulder, okay, that tries to swing it forward, and I'm going to start the pendulum at rest. What I'm doing is I'm doing little tests to check that everything is working, all the physics are working. This is what, is really helpful when you're simulating physical systems. Do these checks, these sanity checks as they call them. Make sure they're working. So let's go to our initial conditions. Here we go. Right now it's 3 pi over 4 and pi over 4. That's the sort of upward position that we've got. So let's instead make it 0, 0. This will start everything at the bottom, right? Let's just make that 0, 0. And if we do nothing right now, if I run this, this should just have a pendulum just hanging down, doing nothing. Look, hanging down, doing nothing. Exactly as we wanted. This is working way too well. I makes it look a little too easy, I'll be honest. I should screw up more. Careful what I wish for. All right, so now that's 0 torque. But if I add a little torque to my shoulder, this should try to swing things forward ever so slightly. It'll create a little bit of a swing, okay? So let's put a torque at the shoulder. That's going to be tau 1. So where did I define tau 1? Right now, tau 1 is this 0 right here, okay? I'm going to change that to a 1, okay? And I don't like this is all on, this is a little bit too sloppy of an inline function, but you can get away with it. I'm going to do a little ... put it on the next line so you can see a little bit more easily with your large font that you have right here. Here, look. Hey, look, it's swinging a little bit. Anyone see that? Okay. Let me change the torque to 3 so it swings a little bit more, okay? It's applying as the constant torque. And so it's going to keep sort of the average position of this top pendulum is going to be a little bit forward, a little bit to the right, okay? And the pendulum down below is kind of swinging around as being jostled about. Neat? Neat, 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 neat. Let's change it to 5. This is just us checking to make sure everything's working okay. Look at this. Bigger torque, so it swings a bit more. All right, let's do 15. All right, there we go. Now we're talking. Wow, okay, we're applying torques, right? That's the first torque, that's the torque at the shoulder. Let's do the torque at the elbow. If we just apply a torque at the elbow, and not at the shoulder, what we should expect to see is that it's sort of the shoulder just kind of jerking up over and over and over again. And like it should be a pretty symmetrical, but everything should jerk up like that. I think. Let's try it. So it'll be 0, and then torque at the elbow, let's just make it 3. Let's see what happens. It is a smaller mass, so it might not behave perfectly symmetrically. Yeah, it's a smaller mass, but see, it's trying to jerk up the shoulder a little bit, right? Okay, that's applying a constant torque at the shoulder. That's perfect, perfect. And there's even that recoil that happens at the top link of the arm too. So that's looking right. That's looking right. And just for if I make them the same mass, it should be, I think, a perfectly like upward symmetrical motion, I believe. Let's double check. So I'm going to change the mass M2 to 1. Okay, and let's rerun it. Not quite. I think I don't think that what I said was true. But anyway. Okay, let's change it back to 0.5. That's working well. I like it. So look at that. Nifty, right? We're applying torques to this multi-body system using Lagrangian mechanics. And we're doing it all on the fly. Hey, we're changing masses. We could change lengths. Here's a fun one. We didn't change lengths. Let's change length L2 to 1.5, friend. What happens? Everything should change, including the animation. Wow. All the inertias are changing. All the animations are changing. Isn't that nifty? Oh, we're so cool. Math is fun, folks, as is mechanical engineering and applied optimal control, but I'm a bit biased. So back to 1.5. Okay. All right. Now we have torques. Let's apply torques as per inverse dynamics. Okay, this is where we're going to have to reshuffle the code around a little bit. Okay, I love what we got here. We can now simulate a double pendulum and animate a double pendulum. I feel like we should make a new piece of code, okay, that now allows us to do feedback control. Okay, so let's save as, create a new script. Let's call it sim inverse dynamics. We'll call it sim inverse dynamics. We'll call it. So what did I call it in case you couldn't see? Sim inverse dynamics. The 14. We're now in the 14th. Okay. So it still derives the equations of motion of a double pendulum and simulates an inverse dynamics controller. Okay. So what I'm going to want to do here is I'm going to want to create a controller that I command accelerations, in this case, to the joints. Okay, back up here, to the joints. Q double dot, keeping in mind that our Q, as we recall from last lecture, Q was theta 1 and theta 2, right? So Q double dot is the acceleration, theta 1 double dot, theta 2 double dot, the acceleration of those two angles, right? A good check to make sure this is all going to be working is, what if we command our accelerations to be 0, right? And if our velocities are 0, this thing should just stay in place, okay? It should not move, all right? That's a good check to make sure you have inverse dynamics working, okay? Irrespective of whether or not this thing starts off in a down position or in some other weird position, it should be applying torques in such a way to keep the pendulum from accelerating. Okay, so some people call this gravity compensation. Okay, because it's compensating for gravity. Even though it's under gravity, we apply torques that prevent it from accelerating. Right? Isn't that neat? I think it's neat. I think it's super cool. All right, so now we have a new script, sim inverse dynamics. So what needs to change? Okay, things that need to change. Now all of a sudden, these torques here, this is where we would set our torques, right? This is going to become a more complicated equation. We don't have to write this in line, okay? It'd be great if we could write this on a different line. We could write it in a whole different function. Oh, sorry, you can't even see anything. I apologize. I didn't look at very much. Okay, we've now saved this file as sim inverse dynamics. I'm now at the dynamics function. This is here are our taus, right? 0 and 3 is what we set them to. These are our DQs, right? These are our DQs. These are our Qs, right? So these are going to become this is going to become more complicated pretty quickly. I don't want it all crammed into this one line of code. So I'm going to break it out into multiple lines of code at the very least. You can make a whole function file for all you wanted, okay? But we're going to show how clean we can do everything. This is pretty right. So first thing I'm going to do is I don't like the fact that I have to say x1:2. I would like to say like q, right? So I'm going to create a new function. I'm going to call it qfunc. And what does it do? It's an inline function. It takes in our current state, x, right? And then it returns our q's, which is 1:2, our first two states, okay? Then I'm going to have a deq function. Same thing, but it's going to return our velocities. That way, it's going to make sense. Oh, here's our q's, here's our deq's, and then here's going to be our taus, right? Okay, x is equal to x3:4, because states 3 and 4 are our velocities, okay? deq-func, right? All right, so then we're going to have our tau-func, right? That's going to take in our current state, and right now we're just going to have it return just 0 and 0, okay? In a vector, in a column vector with 2 elements, 2 rows, okay? So let's write this out. This is going to be qfunc, takes in their state. This is deq-func. Oh, it's a little longer. This is all fine. Oh, here we go. No, this is all fine. It's a little longer on the page than I wanted it to be. And then this is going to be tau-func. Takes in x, okay? And technically speaking, let's see. Oh, and look here. We can replace this x3 and x4. That's deq-func, right? Perfect. Of x. Nice. And this here, m-func, this is here. This x1:2, that's q. Those are your positions, right? That's qfunc of x. Boom. It's just a little long on the page, so I'm going to do a little ellipsis, ... so that way you can see everything, okay? And so you can see everything here. I'm just going to copy all this into the chat so you can follow along. Nifty, neato, awesome, cool. All right. So what do we got? What do we got? What do we got? So this is like a cleaned up version of our dynamics function where we break it down to q's, deq's, and taus. And right now our tau is just 0, 0. Okay. This is no controller, right? Well, we could swap this out with something that is a controller. All right. So how are we going to do this? So first, let's run everything to make sure everything still runs. What am I missing? I'm missing something. 90, missing something. Okay, I'm missing some kind of open and close parenthesis. qfunc, unmatched open parenthesis. Where is that happening? There's open bracket. I'm looking around. Forgot a never-ending bracket. Thank you very much, Marco. There you go. I missed the little empty bracket there. Okay, let's run that. If that works, indeed it does. Indeed it does. And sure enough, if I want to change the torque that I'm applying, if I change this to 5, this will now change my torques to 5 at the 5 at the shoulder, 0 at the elbow, right? Done. All works great. Also, this is neat stuff, right? We're just flopping around pendulums, and we're going to add a controller, right? So that's no controller. What if instead I want an inverse dynamics controller? Okay, so I'm going to copy this. I'm going to say I want an inverse dynamics controller. Okay, how does that work? So I can comment out our previous one. We don't want the no controller. We want to have an inverse dynamics controller. I'm hitting Control R, Control T to add on a Windows machine in order to add a comment. In case you're curious. That's what I'm doing. All right, so for inverse dynamics, we're not going to specifically say, hey, we want 0, 0. What we want is a torque that is derived from our forward dynamics. So here we go. We've got so if we have on the left-hand side, let's go up to here. We're going to have m of q. q double dot plus is equal to f of q, q dot, and tau. We need to solve now for tau, which is a little annoying. I think we can figure it out though pretty easily. This isn't as bad as I feared. It's gonna be just a little bit sloppy, okay? Because what we need to do is we need to find a version of f for which there are no taus, put it on the other side. Okay, there's cleaner ways we could have done this from the beginning, but we'll figure it out, right? We're gonna put everything on the other side except for the taus, right? Okay. So what we're going to do is we're going to break this down into two terms. There's going to be an f of q and q dot, and we'll call that f1, and then f of f2 of tau, right? We can break those into terms that are dependent upon tau and everything else, right? Okay. So how do we do that? So what's going to happen is we're going to say, if we want to figure out what this f1 is, well, that's equal to this, but we substitute in 0 for tau, right? Okay, so what we're going to do is we're going to go to our code. And in our symbolic versions, in our symbolic math here, where do we set f, okay? So here we go. We've got f. Oh, this is actually perfect. Look at this, friends. We can just change this a little bit, right? So we can say that, hey, all this stuff here, that's all the stuff that is not dependent upon tau, right? We're going to call that f1, okay? So here's what we're going to do. We're going to say that f1 is equal to all of this. And then we're going to move this stuff down to the next row, right? Okay. Say f2 is equal to all that, right? Make sense? Make sense? Okay. And then f is just equal to f1 plus f2. So we still have access to f for our computations down below. This should all still work if I run like that. Everything should work just as before. It appears it does. Great. Perfect. Okay. These are external torque terms. Non-conservative torque terms. Okay, these are conservative terms. Conservative terms. Okay. Good. Everything still works, but now if we want to be able to solve for our torques, okay? We want to be able to solve for these things. You'll notice that this function here, tau, you notice, thank goodness, each of these tau, where are our taus? Here you go. Each of these taus, right, are not multiplied by, are not like, they're not signs of these taus. This is just a linear combination of taus. Tau 1 plus tau 2 and a tau 2, right? So we could express this function right here as some matrix B times the vector tau, right? So the vector tau is tau 1 and tau 2, and the vector B would be 1 minus 1, 0, 1. Now, I did that in my head because I know that we have, in our first row, we have positive tau 1, negative tau 2, and in our second row, we have positive tau 2, right? How will we get this automatically? Well, that's just, my friend, that's just the Jacobian. That's just the Jacobian of this term here of f2. B, where B is just the partial derivative. Let me make this a little bigger for you. It's just the partial derivative of f2 with respect to tau. I'll prove it to you, okay? I'll go into our code again. The Jacobian of f2 with respect to tau. What is it, friends? My goodness. Like we know what we're doing here. So if we want to solve for tau, we can put everything else on the other side, and then multiply both sides by the inverse of b. Okay, so let's write that math up. So that means that you have m of q double dot is equal to f1 of q dot plus f2 of tau, right? Okay, we're trying to solve for tau. Okay, we know that m of q double dot is equal to f1 q of q dot plus some matrix b. Think of that as like an input matrix, similar to the x dot is equal to ax plus bu. It's similar to that, right? Times tau, right? Well, let's solve for this. So let's put f1 on the other side. That's m of q double dot minus f1 of q dot is equal to b times tau. Let's multiply both sides. A little color, happy little color here, by b to the minus 1, b to the minus 1. That's a very simple inverse to take, very simple inverse. Okay, and therefore tau, flip it on the other side, tau is equal to b to the minus 1 of m of q double dot minus f1 of q dot. That's it. That's your inverse dynamics. Okay, well, let's write that out in code. Okay, so let's compute what b is right here. So we have our input matrix. B is just the Jacobian of f2, just like we talked about, just like we tried out down here in the command window, of f2 with respect to tau. Oh, glory. Oh, lovely. It's beautiful, beautiful. Okay, so we have b, and for our matrix, so what do we need to do? So in order to actually use these terms, we're going to have to call this equation here as our controller, right? So we have to be able to tell it, hey, here's our B matrix. That's easy. It's just constants. We have that already. You know what we're going to do? We're going to make a MATLAB function. Aha. Ha. Okay. So first, let's say B is currently a symbolic matrix. So if you look at the class of B, sorry, I didn't run it. So the class of, sorry, of that Jacobian, right? That's going to be symbolic class of that answer. So we got to turn it into a floating point number so we can use it later in the code. It's symbolic. So let's say B is equal to double of B. So double precision floating point. Okay. All right. That's your input matrix. We have access to that. Then we're going to need access to this F1 of Q and Q dot. We don't have that as a MATLAB function yet. Well, guess what? We can make it into a MATLAB function. Hey, look. This is where we make MATLAB functions. In this part of the code where we create MATLAB functions. Using a MATLAB function that's called what, friends? MATLAB function. Appropriately enough. Let's call it F1 func. Is a MATLAB function. Where you take an F1 and the variables for it are, well, what are they? They are Q and Q dot. So comma, Q underscore and DQ underscore, Q and Q dot. Done. Now we have F1 func. Oh, great. So we have everything we need. We have a function that we can compute our mass matrix with. We're going to put in our desired Q double dots. We have a function we're going to compute F1 with. We have B. Done. Glorious. So there we go. Now if we go down to defining our controller, oh, look, there's our inverse dynamics controller. Okay. All right. We need to plug, what do we need to put in there? It needs to be, instead it needs to be B to the minus 1. It's literally this equation I got boxed in right there, times the quantity, M underscore func of our Q, and we call this Q func of X. Not sure that's easier, but I don't know. I feel like it's more readable. It's like, hey, this is our function. This is our Q, right? Q function of X times what? DDQ desired. So this is our Q double dot desired. Okay. So we're going to actually make this an input to this function. We'll get to that in a second. But it's Q, we'll call it DDQ desired. All right. That's our desired accelerations. Let's put this on a next line. Minus on the next line. I'm going to minus F1 of Q and Q dot. Okay. So that's F1 of Q func of X. That's Q. And DQ, Q dot. So it's DQ func of X. Okay. Done. That's our inverse dynamics. We've not defined DDQ desired. That's okay. We'll do that in the line above as a constant. So DDQ desired, these are our two accelerations. Acceleration for our shoulder and acceleration for our elbow. Let's make them 0. Okay? 0, 0. Okay? Semicolon. Let's see if this works, friends. This should be a 0 acceleration. What did I screw up? What did I screw up? All right. Tau func X. Did I screw something up? Inverse dynamics. What's yelling at me? Okay, I'm indexing into something incorrectly. F1. We're extremely close, friends. We're going to get this going. It's going to be fun. At least the inverse dynamics controller. Okay. Some kind of indexing error. Index position in position 1 is invalid. Array indices must be positive integers or logical values. Okay, I'm putting something. Okay, so it must be. I must be throwing in something it's expecting as an index, but it's not in fact an index. Right. In which line of code is that happening? Not 967. Okay, it's happening in the inverse dynamics function when I call it. Q func of X. Do we define that? Should be okay. F func. Wait, no, it's the inverse dynamics. It's wait, which function? Which line? 96. It doesn't like line 96 and it doesn't like line 100. Okay, but it happens first in line 96. So it's got to be here. I screwed something up here. F1 should take in 2 things. So this is just a real quick thing. If I just say, why is that not working? Is F1 not being generated correctly? Let's see. X, Q double dot. Let me just make, what I'm going to do is I'm going to try to execute individual parts of this line of code and see what would throw an error. Okay. So what I need to do is create a state vector X. I'm just going to say we have 4 states, you know, two positions, 2 velocities. I'm going to make them zeros. Okay. X, right? And so if I were to say, what is tau func of X? What does it happen, friends? It gives me an error, right? That's not good. Well, why? Why is it not good? Which of these components is bad? Can I do a b to the -1? Will it allow me to do that? It will. Yes, that's the inverse of b. Good job. Will it let me do this part of the function? Okay, will that yell at me? No, that's fine. Okay, that is the inertial matrix. DDQ desired. That's fine. Okay, I'm just copying and pasting. Like, are these things working? This should all work out fine. Yes, indeed it does. Okay, now F1 func. Thank you. Thank you very much, Marco. That's it. I forgot to say F1 func instead of F1 because it's the function that I made. Now let's run it. Good. Nothing is happening. Exactly as predicted. However, you'll notice it's in the down position. Nothing would happen anyway, right? But if I were to take this pendulum and put it into some position where it would normally fall and swing and do kind of crazy things, inverse dynamics should be smart and try to make the acceleration 0. So let me put it into a different initial condition. So all we changed. Thank you, Marco. Got it right. F1 func. That fixed it. All right, now let's go put it in a different position. Where's our initial condition? Let's put it at the position we had before, which is 3 times pi over 4. That's like 45 degrees going up. And then pi over 4, that'll put the second pendulum up another 45 degrees. Let's run it. Hey, look at that. Let me get it out of your way. See that? Shouldn't that be swinging? It's not. because the inverse dynamics is telling you that it wants the accelerations to be 0, right? I'll show you another. So you do this for any pose. Let's do pi over 2, which is like 90 degrees, and then straight out again, that's 0. So it should be pi over 2 and 0. So that means they're both going to be pointing straight out to the right. There we go. Nothing's happening, right? Okay. Now, that's good. So what do we call, when we say we want 0 acceleration under gravity, we will often call this gravity compensation. Literally, the torque is smart enough to know to get rid of the gravity. Isn't that cool? And right now it's got 0 starting acceleration, okay? But that doesn't necessarily mean 0 velocity. The only reason it's 0 velocity is we tell it that our 2 starting velocities are 0. Let me make my starting velocity of my last link like 0.1, okay? A very kind of slow starting velocity, okay? So that second link should keep spinning at constant speed, angular speed, not being accelerated because the acceleration desired is 0. Let's watch what happens, okay? So 0.1, what happens? Look at that. Spinning with constant acceleration. Let's make it 1. Let's make it 1, 2. Let's make it 2. So this thing should be spinning 2 radians per second. That's pretty darn fast, okay? And then, but the accelerations should be kept 0. So everything should be at constant speed. Look at that. Perfect. In spite of all the inertias being swung around, the accelerations are kept perfectly 0 with this inverse dynamics controller. So it's not flopping around doing crazy things, right? So let's make it, no matter the fact that you have all these inertial terms, all these Coriolis terms that should be flopping it around, right? There you go. Look, change it to 5. Look how fast that is. And just to prove it, what happens if we turn off the controller? Okay, if I turn off the controller, so I comment out this tau funk, and then recomment in that tau funk, same initial conditions. What happens? Flop. Isn't that cool? We did it. We made an inverse dynamics controller. Let's turn it back on by recommenting in that. Isn't that amazing? That's really cool. Now, we're at the end of the lecture today, okay? But what we are commanding explicitly are desired accelerations. In fact, what we're going to do is we're going to just, right as we're finishing up here, let's set our initial conditions back to be, where is our initial conditions? Down here. Let's make them all, I'm losing my mind. I want to show it real fast. I want to make them 0 and command a non-0 acceleration to show that it works. Okay, I'm just losing my mind. DDQ desired. Here we go. I'm going to make them 0, 0, 0, 0. Okay. Straight down, both pendulums starting at rest. I'm going to change my DDQ desired for the second link. I'm going to make it 0.1. And this should accelerate only the second link and not the first link. Okay. There we go. Starting to accelerate the first link. And it's not even affecting the second link. Everything is compensating perfectly between those 2 torques to do that. Let's make it 0.5 just so it accelerates faster. It's going to get pretty fast. Look at that. Beautiful. Okay. Now, the only reason that we can do this so perfectly is because we have a fully actuated system. We have unlimited torques. We're asking it to do very reasonable things. And also, that's where operational space control is going to come into play, where we're going to add constraints on our torques. And we might have limitations on the number of actuators that we have, and we want it to move in task space. So that's where we're finished today. Thank you very much for your patience. Went 2 minutes over. I thought it was pretty fun, though. That's pretty neat, right? It's pretty neat. Look at that operational space controller. All right. That takes us to the end of the lecture today. I'm just going to put this at an interesting initial configuration of pi over 2 and 0. And so that way you can watch it do something, you know, kind of neat. Gravity's still on, but our torques are smart. All right, folks. Thanks so much. Have a good day. Good luck finishing up the homework. Thanks, Marco. Good catch with the funk.